Hey everyone, Mr. Houck here. In today's video, we're going to be looking at distance and midpoint in the complex plane, and we're going to be looking at something called DeMoivre's theorem to compute powers of complex numbers. Let's go ahead and get started. So first we're going to look at finding the distance between two complex numbers in the complex plane. So given two complex numbers, it is possible for us to calculate the distance between the two. In fact, we can use both an algebraic and a geometric approach to calculate the distance. Let's first look at the algebraic approach. So, to find the distance between two complex numbers, we can simply calculate the modulus of the difference between those 2 points. Let's look at an example. Let's calculate the distance between 2 plus 3i and 5 minus 2i by calculating the modulus of their difference. Now, an interesting note is that it actually doesn't matter how we take the difference. We can either do 2 plus 3i minus 5 minus 2i, or we can do 5 minus 2i minus 2 plus 3i. I'm just going to go ahead and do 2 plus 3i minus 5 minus 2i, and then we'll take the modulus of that difference. And the reason it doesn't matter which order we take the difference in is because when we take the modulus, we're going to be squaring terms. We know that when we square terms, we're going to get positive results. Okay, so let's go ahead and find the difference between these two complex points. So let's start by doing 2 plus 3i minus 5 minus 2i. All right, well, we know that we can distribute this negative. So doing that, we would get 2 plus 3i minus 5 plus 2i. So again, this is as a result of distributing our minus sign here. Combining like terms, let's combine the real parts. 2 and negative 5 would give us negative 3. Combining the imaginary parts, 3i and 2i would give us 5i. And now that we found the difference between the two complex numbers, let's calculate the modulus. So we know the modulus is the square root of the real part squared plus the imaginary part squared. So the real part, negative 3 squared, plus the imaginary part, which is 5 squared. Negative 3 squared would give us 9, 5 squared would give us 25, and adding those together we get the square root of 34. And the square root of 34 cannot be simplified, so this would be the distance between those 2 points. Now, once again, just to kind of prove it, I said that it doesn't matter if we did 2 plus 3i minus 5 minus 2i for the difference, or 5 minus 2i minus 2 plus 3i for the difference. So let me show that real quick. So this time we'll do 5 minus 2i minus 2 plus 3i. Okay, so 5 minus 2i, let's go ahead and distribute the negative here. That's going to give us minus 2 minus 3i. Combining the real parts, 5 and negative 2 would give us a 3. Combining the imaginary parts, negative 2i and negative 3i would give us minus 5i. And then now let's find the modulus of this difference. So that would be the square root of 3 squared, because 3 is the real part, plus negative 5 squared, because negative 5 is the imaginary part. This would give us 9, this would give us 25, and we can once again see that we're going to get the square root of 34. Okay, so that's how we can algebraically calculate the distance between two complex numbers. Now let's look at how we can geometrically calculate this distance. So to find the distance between two complex numbers graphed in the complex plane, we can simply create a right triangle using the horizontal and vertical distance between the points, and then use Pythagorean's theorem to find the desired distance. So let's use the same points. We have the points 2 plus 3i and 5 minus 2i. I've gone ahead and graphed them here. So here's 2 plus 3i, here's 5 minus 2i, and we want to find the distance between them. So let's look at their horizontal and vertical distance, or the horizontal and vertical components here. Okay, so vertically, horizontally, we can see that we get a 90-degree triangle. The horizontal component there is 3, the vertical component is 5, and using Pythagorean's theorem, let's say that the distance we're looking for is x. Well, notice that x is across from the 90-degree angle, making it the hypotenuse. So we'd have 3 squared plus 5 squared equals x squared. Well, 3 squared is 9, 5 squared is 25. This tells us that x squared is 34, and then taking the square root of both sides, we get that x is the square root of 34. Notice that, as expected, the geometric approach gave us square root of 34. The algebraic approaches also gave us the square root of 34. So it doesn't matter which approach you use. Pick one and make sure that you know how to use it to find the distance between two complex numbers. Now let's talk about finding the midpoint between two complex numbers in the complex plane. Well, it turns out that the midpoint of the line segment that joins two complex numbers is simply the average of the two complex numbers at the endpoints. So let's see this through an example. We want to find the midpoint of the line segment joining the points 1 minus 3i and 7 plus I. So let's go ahead and find the averages. For the real part, and let's do the average of the real part first. Okay. Well, we know what an average is. It's where we add numbers together, divide by however many numbers we added up. So we're adding the real parts together, 1 plus 7. We added 2 real parts together, divide by 2. That would give us 8 over 2, which is 4. Now let's find the imaginary part. Okay, same deal. Let's add the imaginary parts together. Negative 3i and 1i. Well, we added 2 parts together, so divide it by 2. Negative 3, sorry, it should be negative 3i plus 1i. That would give us negative 2i over 2, which will reduce to just negative I. So the midpoint is simply the complex number 4 minus I. Give me the shaded box. There we go. Now, that's going to make a lot of sense because if we look at this line segment over here, if we go and plot 4 minus I, well, here's 1, 2, 3, 4, then minus I, we get this point right here. And we can see that this point is certainly the midpoint of this line segment connecting these two complex points. Nice and simple. All right, the next thing we want to talk about is DeMoivre's theorem and powers of complex numbers. So we've seen how to add, subtract, multiply, and divide complex numbers, but we've not yet had an efficient method to raise complex numbers to powers. Now it turns out that having complex numbers written in polar form allows us to quickly calculate powers of these complex numbers. Let's see why. So let's say that z is r cosine theta plus I sine theta. So we're working in generality here. Let's go ahead and calculate z squared. So just based off of how we've defined z, well then z squared, which is just z times z, is going to be r cosine theta plus I sine theta times itself r cosine theta plus I sine theta. Well, let's remember some things that we investigated in the last video. It turns out that if we multiply two complex numbers together, let's say z and w are two complex numbers, well, the modulus of the product is simply the product of the moduli. And we also saw that the argument of the product, remember the argument is simply the angle between the real axis and the modulus, the argument of the product is the sum of the individual arguments. Okay, so that's some useful and very helpful information for us. The reason that's helpful is because looking here, well, we're trying to multiply two complex numbers. We're multiplying z times itself. So we can multiply the two moduli, so r times r, this would give us r squared. And then we can add the arguments together. So theta plus theta would give us 2 theta. Okay, so z to the second power, this complex number to the second power, is r squared cosine 2 theta plus I sine of 2 theta. And we'll be coming back to this because it's going to be very useful for us as we continue to investigate these powers of complex numbers. Okay, so that was z to the second power. Maybe let's try to calculate z to the third power, see if we can start noticing a pattern. So we know z to the third power. Well, one way that we can define z to the third power is z to the second power times z to the first power. And the reason that's helpful is because we just found out that z to the second power is r squared cosine of 2 theta plus I sine of 2 theta. Now let's go and multiply it times z, and we know z is just r cosine of theta plus I sine of theta. Well, once again, notice we're doing a product of complex numbers, and these complex numbers are in polar form. So I can multiply the moduli, r squared times r, that's r to the third. And we can add the arguments. Argument here is 2 theta. The argument here is 1 theta. We add those together. This would give us the cosine of 3 theta plus I sine of 3 theta. Okay, pretty cool. I think some of y'all are probably noticing exactly what's happening here. But if not, let's do this one last time. So now let's go ahead and calculate z to the fourth. So again, z to the fourth. Well, one way that we could define that is z to the third times z to the first. And we just found out that z to the third is r to the third cosine of 3 theta plus I sine of 3 theta. Times, well, we know z is just r, times the cosine of theta plus I sine of theta. And once again, we're multiplying two complex numbers, this complex number times this complex number. They're written in polar form, so we can multiply the moduli. R to the third times r to the first, that's r to the fourth. And then we can add the arguments. 3 theta plus 1 theta would be 4 theta. All right, so let's look at the pattern here. When we took z and raised it to the second power, the result was r to the second power cosine 2 theta plus I sine 2 theta. When we took z to the third power, the result was r to the third power cosine 3 theta plus I sine 3 theta. When we calculated z to the fourth power, we got r to the fourth power cosine 4 theta plus I sine 4 theta. So in general, now let's work in generality here. In general, if z is r times cosine theta plus I sine theta, and n is any integer, then z to the nth power should be r to the nth power cosine n times theta plus I sine n times theta. And we call this DeMoivre's theorem. Okay, so this is called DeMoivre's theorem. So let's use DeMoivre's theorem to do a couple of example problems. In our first example problem here, let's say that z is the complex number 2 cosine 240 degrees plus I sine 240 degrees. We want to calculate z to the fifth. So, well, using DeMoivre's theorem, z to the fifth should equal r to the fifth cosine 5 theta plus I sine of 5 theta. Let's throw in the pieces that we have. We know that r is 2, so this would be 2 to the fifth power cosine of, well, 5 times theta, we know theta is 240 degrees. So 5 times 240 degrees plus I sine 5 times 240 degrees. All right, 2 to the 5th power, that's 32. Cosine of, and let's see here, 5 times 240 degrees, you multiply those together, you get 1200. So cosine 1200 degrees plus I sine of 1200 degrees. And that would be our result. Notice how much faster that would be than doing, 2 cosine 240 plus I sine 240 times itself 5 times. Or even worse, imagine if we had this number in rectangular form and you tried to raise that to the 5th power. That would get pretty nasty. Speaking of which, let's look at our next example. Here we have z is the complex number, -1 plus square root of 3i. We want to calculate z to the 3rd power. Now what we don't want to do is take -1 plus root 3i to the 3rd power and try to multiply that out. That would get a little bit messy for us. So here's what we could do instead. Let's first convert to polar coordinates. So convert to polar first. Okay. And to convert to polar form, we need to find r, the modulus, and we need to find the angle theta. So we know r, the modulus, is the square root of the real part squared, which is -1 squared, plus the imaginary part squared, which is square root of 3 squared. Well, let's see, -1 squared, that's going to be a +1, so we have the square root of 1 plus, well, square root of 3 squared, that's just 3. 1 plus 3 is 4, and we're pretty fortunate here, that's a perfect square. Square root of 4 is 2. Now let's find the angle theta, the argument. So the angle theta is going to be the inverse tangent of the imaginary part divided by the real part. Well, we know that's going to be the inverse tangent. Now let's see, the imaginary part is square root of 3. So square root of 3 divided by the real part, which is -1. Well, this just gives us the inverse tangent of negative square root of 3 after simplifying. And that means we want to go to our unit circle and find out where is the tangent negative square root of 3. And specifically, since the real part is negative, the imaginary part is positive, when we know negative comma positive, that would be the second quadrant. So where in the second quadrant do we have an angle with a tangent value of negative square root of 3? Well, if we look at our second quadrant here, tangent values, which are in our rectangles, there's our tangent value of negative square root of 3, and it's occurring at 120 degrees, or you could use 2 pi over 3 radians if you wanted to. Let's use 120 degrees. So theta equals 120 degrees. So that means that in polar form, this complex number would be, z would equal 2 cosine 120 degrees plus I sine of 120 degrees. So we've converted to polar coordinates. Now we want to calculate z to the 3rd power, and this is where DeMoivre's theorem is going to kick in. So we know that z to the 3rd power would simply be r to the 3rd, or 2 to the 3rd, cosine of 3 times 120 degrees plus I sine 3 times 120 degrees. Well, let's see, simplifying here, 2 to the 3rd power is 8 cosine of 360 degrees plus I sine of 360 degrees. And this would be perfectly fine to leave it here. This would be in polar coordinates, or since the problem was given to us in rectangular form, we could also go ahead and convert this to rectangular coordinates if we wanted to. Let's see, cosine of 360 degrees. Well, we know 360 degrees right back here, same as 0 degrees. The cosine is 1 and the sine is 0. So the cosine of 360 is 1. The sine of 360, because this is 0, 0 times I is just 0. So we'd have 8 times 1, which is just 8. I don't like that. Give me the shaded in box. There we go. So either of those answers would be acceptable. 8 cosine 360 degrees plus I sine 360 degrees, or just simply 8 converted back to rectangular form.